as mentioned, this is not this section is not in your BANA 2 textbook. It's in your BANA 1, but the material is up on Blackboard as a full chapter that you can use. And let's go for it. So we're going to do analysis of the variance. Some of you may recall the term variance analysis from last semester. Anybody who did you, Heather? You took it on the main campus, didn't you? Did you guys get into any type of variance analysis, F values or anything like that? You did. Okay. Well, we'll do a refresher on it. So there's variance analysis and then the analysis of the variance. And there's really two different reasons you would do that. But the underlying reason for analysis of the variance, or Anova, is that if the variances are the same, you can assume that the means are the same, or you can conclude that the means of the populations are the same, with certainly a So here's what we will do today, is we'll first talk about the experimental design, and we've talked about this a little bit before as far as pre-test and post-test, and then you have this treatment that's applied. And a traditional one there, a classic one there, is you've introduced a new sales plan. You had sales pre-sale, before the sales plan went in, or before the advertising program went in, or before the new manufacturing process went in, and then you take a measurement afterwards, the post, and then the treatment is in between, and you see what happens. That's the classic experimental design, and you can use Anova quite effectively to determine whether there is a difference in the means between the pre and the post. And in some respects, you can actually home in on the variance if you want to figure out, okay, how much variance am I getting in a manufacturing process pre and post? So there's a number of ways you can do this. We'll use a completely randomized design, which just means you have a nice sample size, and then you're selecting, and every person or every subject that you select has an equal opportunity or an equal chance of being selected for the test, either the test group or the control group. And then we'll do some multiple comparisons. So what we'll do is we'll say, okay, first off, is there a difference between these two means? Okay, and more specifically, is there a difference between these two variances? And then you infer from that there is or is not a difference in the means. But then you want to go one step further, and you want to say, okay, which of these is not like the other? And the great thing here is that with your t-test, what you've done, remember the t-test, okay? Generally, you would compare one mean to a second mean. Well, what about it when you get a third mean, a fourth mean, a 20th mean? What do you do then? You would have to run multiple t-tests. So with this, the beauty of this one is, or the great thing about this specific test, Anova, is that you can compare 25 means, and there's a few more tools in there where you can control for external factors. So it's a very, very powerful tool. But the primary difference between the t-test and Anova is that you can run two. You can run two for sure, but you can run 3, 4, 5, 6, and really up to what's called K in this situation. Tee this up a little bit. Okay, there are two types of testing. One is an experimental, and you're actually, it's like being a chemist. We've talked about this before. You're a chemist, you're a scientist, and that's why they call business analytics a statistical science, and that's why it's in the math and science department sometimes as opposed to the business school. And so you have this experimental design where you have a pre and a post, and then you can also do an observational. Now this observational is generally more associated with qualitative, but you can take in observation data, observed information, and turn it into quantifiable or quantitized data. For example, the Likert scale. We talked about that. Is what are your feelings on a scale of 1 to 5? Likert in its purest form is 1 to 7. Do you think it's great? Do you think it stinks? Okay, and so you can quantize feelings. So that's a little bit more the observational aspect. Another observational aspect is you can observe how many times a motion time study. Okay, and you can observe what are the steps that each person takes in. You observe how many steps it takes for a person to complete the process in one situation versus another situation. So that's an observational. So what we're going to do here is we're going to home in on an experimental study, and it always has spillover into observational as well, but we're going to have one or more factors that are going to be influencing, okay, or going to be predicting, okay, are going to be influencing, as I said, the outcome variable of the situation. All right. And then we'll have these cause and effect relationships. For example, a cause and effect is if I put more advertising out into the marketplace, again, traditional. If I put more advertising out in the marketplace, what effect is that going to have on sales, theoretically? It's going to increase, that's right. Okay, hopefully. If it decreases, as we've talked, you got to go find another ad agency. So, some terminology. I got one more here. Here's a little terminology. The treatment is what you actually apply to the situation. Okay, you create a new sales program. You create a new process. You create a new marketing plan. You create a new promotional activity. Okay. And this applies to business to business, B2B. It applies to business to consumer. Consumer packaged goods is an obvious example there, relative to our friends here at P&G. And then it also applies between business to government. So, I mean, the government is actually marketed to because they spend their government represents about 15, depending upon the numbers you look at, about 15 to 20% of all the money that's spent in the United States is spent by the government. And so that's a specific marketplace all into itself. And so you're also looking at the experimental units, which generally is what exactly are you measuring? Are you measuring sales? Are you measuring number of ads? And each one of these has a unit associated with it for the experimental design, and then randomly assigned to experimental units. So you've got to have that. The key. There's two keys in experimental design as far as the basic goes. One is randomness of sampling, and the other one, as we talked last week, is normalcy of distribution. Those are two key areas, and really the basics of the assumptions that need to be not necessarily violated, and that they are, you have to control for them, and then you're exposed to invalidity. But that's a little bit beyond the scope of this course. And there's other courses called research methods where you'll actually dig into sources of invalidity. So here's a classic causal model. Is you have sales, let's put it back into this vernacular, what we talked about. You have sales that occurs here, okay, and this is the dependent or the outcome variable. And then you have X, which is the number of ads that you run. And you can see here, and that's called the independent variable. So this is the X-axis and the Y-axis. And what you do is you're coming along here on the number of ads, okay, and you say, okay, I'm creating the number of ads at this level, and this is my sales. What happens when I double the advertising or increase it by 10%? Does it go up? Does it stay the same? Or does it go down? And that's on the actual outcome variable, which is the number of sales. Now, as we said, this is a visualization. This is data visualization. We'll talk more about data visualization in the next module very heavily, and there's some really fun stuff going on there. Again, geekish, but the State of the Union is tonight, and there will be these Wordle charts or these word bubble charts that'll show both the president, okay, of the United States and what his emphasis is, and then there'll be a congressional response. And I think who's going to do the congressional response? Anybody know that? Who's it? Joiners? Oh, Joni Ernst from Iowa. Oh, we have a lady from Iowa who's going to speak for the other side of the aisle. So it'll be interesting to see what the two groups emphasize as far as what are their plans for next year, or for the next couple of years. It probably, because I'm sure Obama's going to, I would think that he's going to lay out what's going to happen the next 18 months until he has to leave the White House, because thankfully we have term limits on our presidents, and it's always a good thing to refresh the situation. So now, what you see here is you have this pre-treatment, pre-test, okay, post-test, okay, and here is this treatment, and the treatment is you have increased the number of ads. This is a visualization of what experimental design is all about. So far, so good? So here's some more examples. Specific to variance, you can go in and you can say, okay, what is the variance? I have two manufacturing processes, and is less variance better or worse in a manufacturing process? Why? Who said that? Mitch, yes. Yes, because the less variance you have, the less error that you have, at least in a manufacturing situation. However, that being said, could you think, and outside of Mitch, could you think of a situation where, actually there's many situations where you're not getting enough variance? Who might be interested in that? People that make locks would be okay with more variance. Why?
Because you wouldn't want two locks to be the same.
Ooh, interesting. It's an interesting thought. Let me think about that one. Yeah, I've got a little more classical one. In a manufacturing process, if you've got two steel bars, and let's say that you are the there's obviously the high quality guys, but there's also the low quality guys, right? And so the low quality guys say, you know what, a little extra variance, I'm good. Now, you're going to pay a cheaper price, or less expensive price, because it doesn't have quite the quality standards set up. But some people go, you know what, a rebar is a rebar. Okay, as long as it's not too bad, I think I can still get it. I think my customers will still buy it, even at a lower quality, as long as I lower my price. Marketing department, you've got males and females, and you want to understand how many times per day they read, how many times a week per day, how many. Actually, you could apply this to Yahoo or MSN. How many people look at the news more than once a day on Yahoo or MSN? Here we go. How many people look at Facebook more than once a day? All right. So. And it might vary between males and females. All right, so that'd probably be a little more better understanding. And you can actually come in here, and once you figure out how much variation, you can make some conclusions about the means as far as how many times a day men and women, or males and females, access their Facebook page. Here's another one, and this is where you jump from. You can see here there's male, female. Actually, there's a third gender here, so this would actually probably bump into an Anova pretty quick, as opposed to being able to do a straight up variance analysis, because there's male, female, and then there's a third one. It's transgender, and those are the people that do not identify with the sex or the gender of which they were born, and it's a real category. It represents, I think the incidence rate is only about 0.2 or 0.1%, somewhere right around in there. But the government does recognize transgender type of as a whole different sex category. Let's call it gender category. Okay, so now you jump into 3 types, and this could be 4 types, 5 types, 10 types, K, and you'll see the value of K, much like we have the value of N, right? It's just a placeholder for a number that can vary anywhere between and it's usually an integer between that's a whole number between 0 and probably, well, actually 1 and infinity and beyond. And here you want to compare stocks. You have 10 utility stock, and you want to compare 3 types of common stock. And so what were their performances? And so rather than going in and running multiple t-tests to figure out which one was better than the other or which one had less variance, okay, you can go in, hit an Anova, and it'll all lay out for you. It's a great tool. In fact, I'm using that in my research that's coming out hopefully here in the near future on angel tax credits. So, in analysis of variance, what we say is that if the variances are near to the same, okay, the mu's, the population means, are the same. And so you're going to actually go in and you're going to run a test, okay, based upon each of the population samples, X bar, and then your HO, your null hypothesis, is going to be they're all the same. No change. Okay? And a good analogy there as far as null hypothesis, just to bring everybody kind of link back to what we talked about before, is in the U.S. legal system. What is the presumption as soon as you get arrested? You're innocent until proven guilty. So innocence is the null hypothesis, and then as you go through a trial, assuming it gets to trial, there's evidence that's brought forward and statistics and everything else, and then you prove or accept or reject the null hypothesis that that person is not guilty. So that person could indeed be guilty, but you still have to come back and actually accept the alternate hypothesis, and that is done in the jury box when they take a vote. And hopefully you'll get, depending upon the case, you'll get anywhere between 10 and 12 people agreeing that there is the person is guilty. We accept the alternate hypothesis because you've proven it without reasonable doubt. And without reasonable doubt, what's that in our vernacular here? P.05. Right? So every jury is certainly not 100. Well, there are some cases that are cut and dry, but there's a lot of situations, and we're seeing it now. All the DNA evidence that's coming forward from the 1970s and 1980s are doing DNA analysis. Now, clearly, if a person finds that the DNA did not match that person's the DNA at the crime scene, that person's walking. Now, what was the probability that the jury in that situation was wrong? Kind of in hindsight, it was 100%, or near to 100%. So anytime there is this test done and you're rejecting the null and you're accepting the alternate, or vice versa, there's always, always, always room for error. And as business people, we recognize that. And we say, you know what? It is okay to have some level of error or some chance that our decision is going to be wrong. But if you wait for perfect information, how long could it take? Especially if you're trying to figure out, again, we moved it over to India the last time. Okay? In India, there's 700, 800 million people. Do you have to sample, or do you have to talk to all 800 million people in India? The answer is no, because for a couple of reasons, one of which it'd be highly expensive. B, by the time you figured out what they thought, it would be 10 years down the road and it wouldn't matter. Okay? So these are the underlying premises as a conceptual view of Anova. And we're going to keep using the term Anova, so just look at it, and I try to use as much as possible analysis of the variance, but eventually we're just going to go, and that's the way it's talked, Anova. So here's what we do, is we say, if you reject HO, okay, you can conclude that all the population means are different. And we're going to use s squared or variance, small s. And most of the time, we're not going to have the standard deviation of the population. So in this class, we're going to assume kind of more or less real world, and we're going to use the standard deviation for the sample itself. Okay. And what we're saying here is HO, all the population means are different. We cannot conclude. So that means they're all the same, but when you go to the alternate, you conclude that at least one of these, this is really important, at least one of these is different. And as soon as you find one that's different inside all of your different samples or your mu's, okay, you reject HO. But now then the question becomes, okay, well, which one of these is not like the other? And I'm gonna really mess these up. One is called a Bufferoni, and I'm going to give you an example of that so you can figure out which one is not like the other. And the other one is a least squared difference, and they actually call it an LSD. So we're going to do some LSD today. Which is legal in all 50 states, by the way. This test is legal in all 50 states. And the territories. Guam, Puerto Rico. What are the Virgin Islands? I guess another one. What's the other one? We got one more, right? Was it? Ooh, good one. Well, you know, they got a whole new set of rules over there. We'll have to see if this one's legal in there. All right. A couple of assumptions. Okay. First off, obviously, you have to have normalcy of distribution. And in this class, when in doubt, we assume normalcy of distribution because this Anova is known as a parametric test, which means that we have assumed normalcy distribution. Therefore, the empirical rule applies, and all the percentages and probabilities that are associated with the empirical rule and the bell-shaped curve, where you get between plus or minus 1 standard deviation is 68%, plus or minus 2 standard deviations is 95%, más o menos, and then virtually all are included in plus or minus 3 standard deviations. And then everything in between has a value as well. And they must be independent, which means that one does not necessarily is not dependent upon the other to have occurred in order for you to get the results. Okay. All right. And this is just for Anova. And some of this is going to start looking real familiar. Build this up. And so you see here where we're going to compare these three. Well, how is that? These three sample means, and we're going to use the standard deviation squared, which becomes the variance, and then we're going to apply n as necessary in order to conclude whether the variances are the same or different, and then you would infer or you would conclude that the means are the same. And let's talk about that just a little bit, why you should accept that. This is just one of those things where you just accept that it's part of the test, but here's the underlying discussion behind the situation. Okay, so if you find that these means, okay, and that specific sample have different variations or different variances, s squared or sigma squared, okay, you can see that there's not an intersection between, for example, this one, x2, and x3. Because it goes like this, right? All right. And then it goes like that. All right. So x does not fall here. x3 does not fall under that curve. So therefore, we conclude that they're different. And so you would say that HO is false. You would reject HO if, in fact, visually, x3 does not fall within the distribution curve associated with x bar sub 2. And this one is different than the others. X2 is different than the others. Okay. Now then you come in here and say, okay, what about X3? Right? X3, that also does not fall under here. So who's different of these three, X1, X2, X3? Which one of these is not like the other two? Yeah. Who said that? Why? Yep. It doesn't fall under this curve, and it doesn't fall under this curve. That's right. We'll give you. I'll give you a few more visuals on how you can go in, and this is kind of the basics of data visualization in many respects. Good. Thank you, Michael. Do you my mic or Michael? You okay? Call you that then. And so what we do is we look at the F value associated with this analysis, and the F value is the value. It's much like when we did a t distribution, we did a t value. This is an F value. Same old, same old. The only difference here, okay, and it's a family just like we had before, is that you can't get a negative F value. And so, therefore, we'll get into this a little bit further as far as which one becomes the numerator, which one's the denominator. But regardless, you can see here that each one of these has a frequency. And what we do is we also rely a little more heavily on the degrees of freedom. Remember the degrees of freedom, n-1? Okay. If you're doing more than 3, if you're doing more than 2 samples, you're looking at a k-1 for the numerator and the denominator. And does anybody need a refresher real quickly on degrees of freedom? Degrees of freedom, in case you, well, this might be helpful for some people here. But if you are, anybody ever watch the horse races? Watch the horse races? Okay. Is that every time you assign a horse or a subject into a slot, or take a sample from the population and assign it to a slot, and you started out with 10, how much flexibility do you have left numerically once you assign the first person, or the first horse in this case, into that slot? 9, n-1. It also applies to a Little League team. Anybody ever played Little League baseball? Anybody played Little League anything? Okay, Little League baseball. How many players on a Little League baseball field? 10 most of the time. They have 4 outfielders in Little League. Okay, and little Joey shows up. And you assign him at random to one of the 10 slots. How much flexibility do you have once you assign? What was his name? I said Joey. Joey, thank you. Joey, and that was actually a player on my team. Joey to that slot, n-1. Next person comes in, and it's Shaniqua, and you assign Shaniqua to left field, and you have one less degree of freedom. Let's see. You also, just like you did in the normal distribution, the normal distribution curve, where we used a t or a z. These are asymptotic, meaning they never reach the actual x-axis. I think that's it. Oh, it's in a continuous, so it can be any value. It doesn't have to be a whole number. Let's let this build. Now, what we do with a variance analysis is, just like before, we set up a reject and a do not reject zone. All right. Now, we're not going to spend a lot of time on reject and do not reject zones here in this course. Hopefully, you got that in the basics course and you got it down, because what we're going to do is we're going to rely on the Minitab software. I'll give you an example of that. And so what you have, and this is basically, remember the variance 1 over variance 2, okay? And when you have 3 or more samples, you kind of blend those variances and divide by the other. Okay, so it's just a little bit different technique. Don't get overly concerned about this because the computer does it for you. But I'm going to give you a little bit of the theory in behind what the computer is doing so you can appreciate what you don't have to do, and the computer can do this for you because computers crunch numbers and reports, and people crunch decisions. So just like before, you have this critical value, only instead of t sub alpha, and alpha is what you're running the test at, p.05, p.10, p.01, p.07 if you're trying to get creative. And you have this do not reject HO. And the F value, you're going to actually, if you're actually going to calculate a test statistic, the F value, and then you're going to apply it against this critical value. And if, for example, the F value on here, okay, and this is 3, the critical value associated with that significance level, let's just say it's 3, and then you calculate for the 3 or 4 or 10 samples, okay, that the value is 2. You run it against this model, right? Okay, and where do you fall if this is 3 and your test statistic is 2? Yeah, you do not reject HO. There's not enough evidence to reject HO. However, if this blended F value, F statistic value for 3 or more, and I'll show you 2 or more, and then I'll advance to 3 or more here in a second. If it ends up at 5, you're going to accept or reject the null. You're going to reject it. And most likely, but you got to come back and you got to accept or reject the alternate hypothesis as well. It's no different than before. I don't know if you remember this, but I don't know. Oh, may I use your water bottle? Mm-hmm. Okay. All right, your water bottle. This is for those who are online. You can get a chance to appreciate this. This water bottle is now the F statistic test, right? And you go do, 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 and that water bottle falls in the do not reject zone. Okay. Your test statistic. Okay. What do? You reject. Okay. If this test statistic used to be a water bottle, I've now declared it the test statistic, falls here, you reject. Okay. And you are now our water bottle again. I'm sorry? You what? Oh, we can do this with the stapler too. Oh, okay. Yeah. Okay, stapler. Okay, we can do this with a stapler too. Yes. Okay, got a stapler. Okay, we take a stapler, and it falls in the do not reject zone. All right. This is actually not a stapler anymore. This is now the F test statistic. The F test statistic falls right in here. Do not reject HO. Right. Now it falls out here. You take your test statistic, run it against here, and you can take any object of your choosing, as long as you can put in your right or left hand. All right. And here's what you do. This is a table. Don't get too involved in this table, but basically what you do is you have the mean square of the treatment, the mean square of the error, and divide one by the other. And this is the technique in which you're blending the variances of the 3 or more samples that are out there. And then you come up, you have your degrees of freedom, okay? And just like normal, and here are some of the, and then from that you'll get a p-value. Remember the F chart? Hopefully you remember the F chart, just like the T chart. You take that F value, you take that test statistic, you run it against the chart itself, and you come up with a p-value associated with that test, as far as whether the differences are significant or not. And anytime you see a value less than p.05, what are you going to do with HO most of the time? You're going to reject. Exactly. There's something to write home to Aunt Emma about. All right? I think there was somebody had an Aunt Jane. Who had the Aunt Jane? Maybe that was the. I don't know. Ryan, what's your auntie's name? Do you have an auntie? Ryan. Thomas. I was looking from behind you. Actually, from the behind you look the same. Yeah. Thomas. What? Jen. Aunt Jen. If she says, "Hey, I only want to hear from you if you get something significant," all right? And Aunt Jen, and she says, "But don't write me unless you found something that's of importance." And the only way I know this is if it's and you say, "Okay, fine." If it's less than P.05, she says, "I don't care about P.05, P.10. Just if you think it's significant, tell me about it." But you're going to take that and you're going to say, "Okay, P.05 is less than P.05, something to write home to Aunt Jen about," and you're rejecting HO, which means they are different. Okay. You can also apply this to uncles, aunts, cousins, nephews, or grandparents. Anybody a grandparent here? Kidding. I'm not yet. I'm kind of hoping that things start turning out in the next couple of years here. So they got a house and they got 2 bedrooms. They got to fill it with something, right? And they're married. That's always good. So here, this is our hypothesis for an Anova analysis. Mu1 equals mu2 equals mu3. And HA is, these are not all equal, meaning at least one of these is not like the other statistically. And we did this MSTR, MSE, we did this blended F for 3, 4, 5, 10 sort of variances and also sample sizes. We created our rejection rule. This is the critical value approach. I'm going to do the critical value first. Or actually, let's do the p-value first. If you set up your standard at p.05 and you determine that your value comes in at p.08, do you reject or accept the null hypothesis? P.08, your bogey, your main number is p.05. Are you going to accept? Your standard is p.05. You're going to accept or reject the null if it comes in at p.08. What are you going to do? P.08, and your you would you
I thought it was less than you normally reject.
Oh no. Keep in mind that in order to reject, it has to be less than what you've set up in order to reject the null hypothesis. So if you set it up at p.05 and you determine that your p-value for the actual test statistic comes in at p.08, 09.40, okay, you're going to actually, if it comes higher, you would not reject HO.
Right, so you'd accept, right?
So you would accept, that's right. Okay. Very good. Yes. Yeah, see, thank you. I was just testing you. I'm going to take that one off the video. All right. No, that was good. That was good. That was a good discussion. Yes. You would not accept or you would reject.
Okay.
No, you would accept or you would not reject.
Wait, I was like,
Let's just stick with reject or accept.
okay.
We're going to
Accept.
That's right. Because it's greater than p.05. If it comes in at p.03, are you going to accept or reject? That's right. Good. Thank you. Have we ever met before? No. Yeah. All right. So now let's start out with just 2 samples. And I'll start out with 2, and then I'll take it to 3. This will look familiar to many of you because we did Anova in the BANA course, or not an Anova. We did analysis of the variance in the BANA course, not an Anova. And in the I think on the main campus they don't go through analysis variance. They stop at chapter 10. But let's talk about that. Is that here you have two samples, okay, and you're trying to figure out whether these variances are the same or different, right? And if the variance, which is sigma, okay, this is the population, sigma sub 1 is equal to sigma sub 2, okay, you would say that HO is valid. If they're not, you would reject HO and you would have to come in and accept or reject the alternate. And this is on variance. And keep in mind, these are standard deviations, and then you just square those standard deviations. And here is the formula that you create for your test statistic. It's just your F value. You're going to create that F value statistic, the stapler, the water bottle. What else did we use? Did we use anything else? Yeah, we used the stapler and the water bottle. Oh, and we used this pointer here too today. Okay, and this is your test statistic that you're going to create, and you're going to run it against the model, the accept, do not, the reject, accept, okay, sort of distribution, just like we did with T. And here's how you calculate that. All right. And this is when you square it, it's called the variance. And so what I want to do here is go through this exercise and pull out your worksheet if you wouldn't mind. And for those who are listening on the tape, I've loaded this worksheet as well, and you can print it out. And I print it on 2 sides because we'll do 2 of these problems. And what I'd like to do is for you to work in your groups really quickly on each one, the first, let's go the first 4. And then we'll do methodology together. So given this scenario here, what is the problem statement? You can read through that, okay, and work in your teams. And what is the purpose of this research? What question or questions are you trying to answer? It's all in here somewhere. Okay, and then what is your hypothesis? Let's go mathematically to start out, and then we'll convert that to just regular written language after we come back. All right, so let's pick this up where we left off. Based upon what you're seeing in this problem here, limo driver, what would be a legitimate or a reasonable problem statement for it? It is a research project. This happens every day. This is actually called operations research, operations management. It's you want to find the shortest distance between where you're going to where you're going. UPS does this all the time. In fact, I don't know if you ever heard the term, the thought that UPS, the drivers are most always make right turns. Okay, because it's longer, but they don't have to wait for lights. So someone really had their thinking cap on with that one. Okay, although I asked the UPS driver, he says, "Yeah, it applies most of the time." All right, so what is the problem statement? Who wants to take this problem statement? Petra already gave hers. Who's got one that they want to volunteer here? Anybody? Yes, Michael.
The president's comparing 2 different routes to see which is quicker.
Yeah, you want preparing 2 different routes to see which is quicker. And why would that person do that? Why would the person do that?
Be more efficient.
Yeah, because the purpose is because you want to be most efficient. You want to have customer satisfaction, as Petra said. Okay, what would be the research question that you're doing here, or that you're setting up here, that you want to investigate? The question, not the hypothesis, the question. Yes, which route is fastest? Good. Very simple. Or if you're on a meter, which one is the longest, because you want to maximize your earnings that day. And if it takes an extra 5 minutes, what does it matter, right? But if you do 5 minutes every day for 365 days a year, a little more revenue. But again, I synthesize it. Yes, Brenna. Is it Brenna? Is that right?
Yeah.
Okay, good.
Are we supposed to have like 2 questions, for every case study that we do? Should we always have?
No. You'll generally, for what we're doing here, you'll generally have 1, maybe 2. Okay, just for your case write-ups and when you're doing your presentation, it's a great question. Is I would keep it as tight as possible. Go for 1 question, 1 hypothesis. Okay, and prove, disprove, accept, reject the hypothesis. And then what are your findings? What are your recommendations based upon the question? And as long as everything links back to your question and your problem, you've completed your research project, right? So generally, you want to keep it pretty narrow. For example, I have only one. I have 2 hypotheses in my dissertation. I have one is do tax credits matter as far as creating incrementally new jobs? Does it matter? The hypothesis is the null is it does not create new jobs. The alternate is it does create new jobs. And then I created a methodology. It's actually going to be a little bit, this is kind of like the next level up. It's going to be analysis of the covariate, controlling for population, GDP as the covariates, and I'm going to do a repeated measures, and it's going to be longitudinal. So that would be the methodology, but that's way beyond this course. So what we want to do here is the methodology. What would be the methodology here then? Yes. Okay, you drove the routes, and then what would what are you actually going to do though? You're going to time it, okay, and you're going to collect that data. Are you going to do it just once or twice? Maybe more than that. Yeah, you're going to do a bunch of samples. All right. Once you get those samples, what is your what would be the methodology or the approach that you would actually use to test whether those numbers are the same or different? Anova. I'm going to run an Anova at P.05. In fact, I think we ran that one at P.10, correct? And the variables that we set up, the variable that we set up was one was time, and the other one was a route. And so we concluded. And this is from actually from a printout from Minitab, and this is a graphical representation. And you see here that the p-value is 0.081. All right, 0.08. All right, and you set your here we go. This is going to be we're going to do slightly different. I'm going to go back to Petra. All right, but we had our bogey, our standard was P.10. So now, do we accept or reject the null? Wait, our bogey was P.10, and your test statistic came in at P.08. Yes. Yes. You'd reject the null hypothesis, right? There was sufficient evidence to indicate that you should not accept the null hypothesis. And in fact, you can see this visually, okay, where, okay, you can see where the variance is. There's intersection right here. And so you can see it visually that those numbers are indeed looking as though they're different, okay? Because when you come in here and you look and you draw this straight line, here we go. Oh gosh, let me get over here. And get in one place. When you see this straight line here, let me get a better angle on this, okay? This right here, okay, does not fall. This range does not fall, okay? Or this number here does not fall within the range down here. And also, very clearly, this one might fall. You can make a case for that. But this one definitely, okay, doesn't fall within the range for Route 25. So that's a visualization of what you've been using previously, which were distribution, and now you're just looking at these on a comparing the two with their ranges, the confidence interval. Okay. Let me go through another one. All right. Now I'm going to bump it up to 3. And so we have these. What we have here, the example we have here. Boy, that thing keeps moving around on me. Put that in one place. Okay. All right. So what we have here is we have this experiment. We are trying to. We're auto. What do we have? Auto zones around here. We got auto zones around here. Pep boys. And they carry inventory, and they're trying to figure out whether they should carry wax 1, or wax 2, or wax 3. Okay. So they're going to put the wax on. Okay, and then they're going to run it through this the car wash, and the wax obviously comes off. So you wax on, you wax off. So that's the treatment, is you wax off, right? And you're going to do that for a number of times, and you're going to do them all pretty much. I think we do each of them 5 times. Okay, and you're going to repeat that, and you're going to get a sample each side, and then you're going to measure how much of a shine or how much what the wax coating, did it show signs of deterioration or not. And this can be applied to anything that's out there. I mean, this is just, a real simple business example where they're trying to figure out, okay, which product should I carry on my shelves in a retail store? And here's a great question: are the 3 waxes equally effective? You can approach it from a null perspective as well when you ask your question. And so your null hypothesis here, they are all the same. Okay, mu sub 1 is equal to mu sub 2 is equal to mu sub 3. And so here, kind of going back to the experimental design, here's your treatment. That's the wax. And then you're going to apply washes, and you're going to take a measurement on how much of the shine has deteriorated after 5 washes. Compare the 3 to each other. Now, before you would have had it done 1, 2, 3, 1, 2. You probably had done 6 t-tests, but you can you just run an Anova randomized design, and you come up with your sample variances. And you have your sample means. And so now the question is, are these means, these sample means, relative to each of their populations, are they the same or are they different? Does mu sub 1 equal mu sub 2 equal mu sub 3? And that's what we're going to determine here. Here's our hypothesis. Mu sub 1 is type 1, type 2, type 3, and I don't know what 3 waxes. There's turtle wax, there's armor all, and there's, let's call it rabbit wax or something. I don't know. What's a third? Armor all, and what's a third wax? No. Some other wax. So you're trying to decide, and you're going, and it's a reasonable. This is a reasonable test, right? Once just find, okay, which ones are my, and you're asking yourself, which ones are my customers going to be most satisfied with when I put it on the shelf, based upon its shine, the ability to hold shine after 5 washes. We go through these calculations, and these are the calculations used to blend the variances for each one of those samples. Okay, and I don't want to get into the math here because the software is going to do this for you. And so what you decide is if that p-value is, we're running this at p.05, if that p-value is less than 0.05, something's going on. Time to write and gen. We're going to reject HO. And here we can use the critical value approach. We're going to look at the p-value. As soon as you get a report, and I've got an example of the report here that hopefully we'll get to today, but if not, we'll get to it Thursday. Is when you get the report, the first thing you look for is the p-value. Okay, there's going to be a few different. There's probably going to be a few different p-values depending upon. There may be more than one p-value depending upon which test you're doing. Okay, whether you're doing a legit, multiple regression, on and on and on. But you always go look for that p-value right off the bat, and then you can decide whether to accept or reject based upon the standard that you set up. And just so you know, the p-value, the lower the p-value, the higher the f value, the higher the test statistic. Okay. And so we decide here that the f at 3.89, it's 3.89, based upon the f distribution chart I showed you before, that would be in the back of the book. But the good news here is the tables are loaded into the computer, so you don't have to do any of this stuff. Just kind of know what's going on behind the scenes. And then you create a blended numerator and a blended denominator, degrees of freedom. And here's what you come up with. 0.939, here was your bogey. F, this was your F, 3.89. Is this number lower or higher? Is your test statistic lower or higher? It actually ended up being 0.42. And here's a sample output from the software. And I think I've got some runs. So here's the p-value. So first thing you do, and this is what a lot of the reports will look like. This is just a sample. I've got the one from Minitab that I'll show you here in a second. And you go 0.42. Here's your F statistic. Okay, your test statistic. You knew that the well, you kind of knew that it was what was it, 3? Was it 2 or 3? Yeah, was the critical value. It's less than the critical value, and as you might expect, it's a 0.42. So you can see as this number goes down, the p-value goes up. Okay? So there's no evidence to reject the null hypothesis. Okay. Yes. It was I was up till 1 last night, so sorry. Apparently they had another. Anybody watch Scorpion? Another Scorpion on last night after I got done. I was like, oh, okay. Anyway, okay. So here's what's going on. 3.89. Can I bring it back to where we started? 3.89. This is your alpha value at 3.89. We came in at a point. Your alpha value here was 0.05, right? And we came in at 0.42. No, it was. Is that right? Yeah, your F value was 3.89, right? And we came in at F value that would fall down in here. And this is actually, I ran a report last night, and this is actually how you'd see it from Minitab. So what's the first thing you look for? There's a couple things you can go toward to figure out that these are all the same. Okay, but what's the first thing you look for here? Hopefully I have it. Yeah, good. What's the first thing you look for here? P-value, 0.418. Is that higher than 0.05 or lower than 0.05? It's higher. Therefore, we come to the same conclusion. 0.418. No, you're right. It's higher than point. It's okay. It's okay. No. This is. I mean, again, if you're up till 2 o'clock in the morning, 1 o'clock in the morning, this do not reject, accept, no evidence to reject. You know, those sorts of things. All discussion. It gets a little crazy sometimes. Okay. And so you look right here, and you get then this is an actual printout. And here's wax 1, wax 2, wax 3. And here's another way you could figure this out: the R squared. Okay. There's no correlation between those three. So, you know, your R squared is 0. So that's another indicator. But I would go right to that p-value. And if that's higher or lower than your bogey, you can make a decision. And so what is the decision in this situation? It doesn't matter. But then what's your business decision? You still got to make it. You still got to figure out which one of the three you're going to put on the shelf. That might be it. Yes, you could go cost. What else could you do? What is it? Whichever one has the highest margin. Whichever one, the sales guy came in and bought you a nice steak dinner the last time you were in, so you say, this is close enough. I'll just go with my buddy. And here you can also see where this intersects here and intersects here. This intersects here and back here. And so this is another visual based purely on the mean. And so you can see these confidence intervals. So you can see there's intersection. So they're all the same. And those are actual printouts, and we'll work on those Thursday. Here's another way to look at it. This is the Fisher formula, and you can see that the intersection is still occurring here. Thank you for calling me on that. I was up till